Thanks for joining us, everyone. We'll be starting shortly. All right, so we'll get things started. Thanks for joining us today. We'll be starting the webinar in just a few moments. My name is Tina Fabiano, and I'm on the enDAQ Marketing and Engagement team. In a minute, Steve Hanley, our Vice President of Product, will be presenting today's webinar and Q&A session on custom analysis of your real shock and vibration data with Python in the enDAQ library. We're really excited to be demonstrating how to efficiently customize and adapt your real data into actionable reports using Python in our open source library. In this webinar, Steve will use real data submitted by the enDAQ community to show you how to generate FFTs and PSDs and shock response spectra and a few other reports to give you the exact data you need for your specific application. All of this will be done using a Google Colab notebook, which we'll provide a link to in the chat. You'll be able to make a copy of what you see today and use some of the customization immediately for your own data. In addition to Steve, we also have Becker Alcati, David Stokes, Connor Flanagan, and Sam Ragusa with us as panelists. They're all on the enDAQ software team who developed this library, so we're excited to have them with us to answer your questions as they are incredibly knowledgeable on this topic. This is a 45-minute session. As you're watching the webinar, don't hesitate to use the question and answer button, labeled as Q&A, right at the bottom of the screen. The software team is monitoring the questions that come in and will be able to type answers to some of them in real time. Then Steve and the team will answer any other questions at the end of the webinar. We'll also have some poll questions for you to answer, and at the very end, we'll launch a post-webinar survey. We'd love to have your feedback so we can make sure we're providing you with relevant resources around this topic, and so we can continue to improve our content. We're really excited to be running this webinar today, answering your questions and helping you customize and adapt your shock and vibration analysis using Python in our enDAQ open source library. So with all that, I'm happy to introduce Steve Hanley, who'll be taking it from here.
Thank you, Tina. Welcome everyone to our 5th webinar in this series. I do want to start a quick poll question as I explain what we've previously covered as well as what we're going to be covering today. So I just want to get a sense who has attended some of our previous webinars. Do you have any familiarity with Python? And do you have any of our devices? No right answer. Just help me as I tailor the discussion today. But to recap, we've gone through some introductions to Python. We've gone through some basic data analysis in Python and plotting. And then a month ago, we highlighted our new library that we were really excited to release. And now we're going to be doing more examples. So today, yeah, I think I have that poll question going. Does anyone see that? No one's answered it, but that's okay. Do you have you attended previous webinars? Are you new to Python? And do you have any of our devices? Is that going? Do you see that, Tina?
I can see it on my screen. Maybe we should just relaunch it.
Okay. I will relaunch the poll. All right. Hopefully people see that and answer that. If not, I will continue. There we go. We got a couple people. All right. So we have a good mix here. And this is good. So there's a lot of you that have been to previous webinars and a lot that haven't. And so that's reminded me, and I want to remind all of you that I need to make sure this is relevant to both audiences. So some of you haven't been to our previous webinars. I want to kind of highlight some functionality that I've shown before, but also for those that have been to the webinars, I want to do some stuff today that's a little different. So I'll share those results. And what am I going to do today that's a little different? Well, we asked you when you signed up for this, you know, what examples would you like us to see or to demonstrate for you? And overwhelmingly, it got a lot of people asking for Fourier transforms, frequency analysis, FFT. You know, a lot of people said PSD as well, but there was more people that wanted the more kind of expected FFT. And admittedly, we didn't have any functionality in our library for that, and I had to cover that in the past. So I'm going to spend a fair bit of time today on FFTs and PSDs. Then a few of you wanted shock response spectrums, which I've covered in the past, but admittedly, I probably made it too complex to do all these integrations and filtering. So I'm just doing two really basic examples today. There are some people that want to do peak analysis. So I have a data set that has a few different shock events and how do you find the peak and then analyze it. And then at the end, I'm going to highlight our new batch library that we're working on to batch process many, many files. So as we go through this, though, Tina's, I think, sharing the link. Please open this in another screen. Most people have two screens, and play with this as you go, and follow along as we go. So let's get into it. So first, again, this open source library is available on PyPI. You can install it via pip install enDAQ, and away you go. So check that out. In Google Colab, I do need to do the silly exit thing to restart my runtime after installing it because it loads Python or pandas initially. So, but if you're running locally, you won't need to do that. And once it's installed, you don't need to install it every time. So once it's installed, you import it, as well as some other libraries here like NumPy, Pandas, and SciPy. All right, so the first example is let's make a simple sine wave. And if you guys are familiar with NumPy, I'm making a time array from 0 to 2 seconds with 200 data points. And I'm saying the endpoint equals false. So I'll have a sample rate of 100 hertz, which is what I expect and want to see. Then I make a data frame off that, and I add a couple different lines to it. So I want a sine wave of 0.8 G at 2 hertz, a sine wave of 1 G at 3 hertz, and you see the labels here. And now I have a nice data frame with a few different sine waves. So I can plot that real easily here. And so these are a few different sine waves plotted in Plotly. Now, first thing you want to do is some frequency analysis. And we have a library, or sorry, a function called PSD.welch, which does a PSD calculation of power spectral density. And if I do that calculation, I specify a bin width 0.5 hertz. I then plot it. I get the resulting PSD. And now, a couple of things you may notice. For one, the frequencies are spot on what we'd expect. You know, there's this 0.3 G at 7 hertz. That's exactly there. Another one at 6 hertz and 4 hertz. So you see the frequency content is correct, but my amplitude's a little different and not maybe what you expect. Now, this is something that a lot of people kind of remark on when they see a PSD is, what the heck is G squared per hertz? I'll explain a little bit more of that in a second. But you can actually take this output and scale it to make it look like an FFT. And the way you do that is I have some bullets here to show that exactly how it's done. But you want the scaling not to be a density, but Parsifal's theorem. So it's going to be, instead of G squared per hertz, it'll be G squared. Then we want to use a different windowing method. You know, PSDs are calculated by basically averaging a bunch of FFTs together that are overlapped with a window applied. We don't want that windowing. So we'll do a boxcar. We want a very fine bin width. And then we want to scale from G squared to G peak. And remember, in a PSD, the area under the curve is RMS. So we also need to multiply by square root of 2, and then you get the peak. So if I do that, again, using our function, just adding these parameters and scaling it, I get an FFT that I'm expecting. So here's my sine wave at 0.8 G at 2 hertz. I see a peak exactly there. You know, this other one, 1 G at 3 hertz. I see it exactly at these locations that I expect. So this is great. Now let's get some real world data. So this is data from one of our devices. And if you remember from the poll, that's why I asked it, half of you have our devices, half of you don't. So I'll show, there's a couple examples when I'm loading data from our device. And there's a couple examples where I'm loading from a CSV. But once you've loaded the data, it's a drop-in replacement on all the calculations. So if you do have data from our device, though, this is a helpful function. It's called getDoc. So it loads the data into an object. And then you can kind of see the contents of it in this function getChannel table. And then you could pull out the data frame of the actual, acceleration data or temperature data or whatever it is with the 2pandas function, which I did here. Then I use another function we have in our library, which I went through extensively last webinar, which is this rolling min, mean, max envelope. So it plots a bunch of bars from the min to the max. So when you're zoomed out like this, it looks the same as if you had plotted all the data, yet it didn't have to necessarily plot all the data. So it's more interactive and responsive without having to plot all the data, yet it will look the same. So here it is, the data set. This is what we do when we calibrate our devices. We shake it at 10 Gs at 100 Hertz, and then we shake it at 4 Gs at 150 Hertz. I forget. Here's another function now where I'm just actually plotting around the peak, 500 data points, and you see this really clean sine wave. And this is before calibration, so the peak is at around 2.3 Gs, not exactly the 10.3, not exactly the 10 that we're exciting it at. So then when we apply the calibration, we're applying like a 0.95 calibration. All right, now let's do that FFT using our PSD function. So I'm going to provide here the input as the acceleration data, but from time 4.5 to 9.5 seconds. You know, if you remember, this is a full time range. So if I apply the full time range into my FFT, I have some dead times here. I also have some time at 100 Hertz and time at 150 Hertz. So I want to focus just in this area here. And then I do those parameters I specified before, the scaling, the windowing, et cetera, and then I get my FFT output. And this is great. I have an FFT of 10 Gs, 10.3 Gs at exactly 100 Hertz. Even if you look at just the y-axis, it's about 0.12 G. You know, there's a little bit of transverse here, and you see here, this is the y-axis data, which is around 0.12 G. So this is great. My FFT is how I expect. Now, there are a lot of different options in Python to compute an FFT. So I want to compare a few of these options now. And this is something that I really dove into like the last couple of days, and I've learned a lot, and I'm excited to share this with all of you. So the first function I made is what I've been using previously. It's basically computing that PSD and then scaling the output to look like an FFT. And remember, PSDs, again, are computed by doing a series of FFTs and averaging them. So it's still an FFT in a way. Then I'm using NumPy's built-in FFT functions here. And then I made another function here that uses the FFTW algorithm, which Becker, one of our software engineers, told me that stands for fastest Fourier transform in the West, which I thought he was joking. He still might be joking, and he wanted me to see if I'd say it out loud. But I think that is actually what it stands for. This is the algorithm developed by MIT. It's what MATLAB uses. It's generally known as the fastest algorithm out there for computing an FFT. So now I'm going to use that to get the FFT of my data here. Again, I'm just passing in the pandas data frame of the time history, again, from 4.5 to 9.5 seconds, and then plotting the output. I zoomed in the plot to just go from 80 to 120 Hertz. And I see my nice peak exactly at 100 Hertz and 10.3 Gs. So great. The other benefit, though, is now I'm using the more traditional FFT libraries, so I get phase response. And you see here the phase as we go through 100 Hertz that's almost a 360-degree difference, which is good. And phase is helpful when you're doing some frequency analysis. It's not always needed, though, but that is a big point, is that when you actually compute the FFT directly, as opposed to doing the Welch's method, you will get the phase response. All right, now let's do a comparison between these three different approaches. So I'm going to make another simple sine wave again that's fabricated. And now I'm going to use a relatively long one. It's a little over 1 million data points. And I'm going to add 3 sine waves to it. A 10G at 100 Hertz, an 8G at 99 Hertz, and a 6G wave at 100.25 Hertz. If I plot that, I'm not going to plot the whole thing because it's 1 million data points, so that wouldn't really work well. But I'm just going to plot basically the first cycle. And now, you don't necessarily need to look at this. Well, you can look at this code, but in this code, I'm not going to go walk through it line by line, but looping through a series of different lengths. So 2 to the power of 14, and then a prime number around that, and 2 to the 17th, and then a prime number around that, and then 2 to the 20th, and then a prime number around that. So if you know FFTs, you know that they do well when it's a power of 2 length, and they don't do so well for prime numbers. So I'm trying to compare the best and worst case. And so I'm looping through these different lengths, and I'm computing these FFTs, and I'm timing it. So now I can plot it. So there's a few different things I did. The first one is using the Welch's method, and that was what we are using in our PSD, and I'm explicitly defining a bin width of 0.5 hertz. So what that means is it's taking a series of FFTs of length of 2 seconds. Did I do that right? And then it's averaging them together. But then in this one, the Welch's method is from here on out, every bin width is going to be the length of 1 over the period of the full time range. So what can we tell from this plot here is that FFTW, when I first plotted this, actually performs the worst, but that's because there is some overhead associated with how I implemented it. So it can be optimized, and you see here that's when I'm not counting the overhead to convert my data in such a way, and I'm using a different built-in approach to doing this computation. And when you do that, then you do get pretty good results of FFTW being the fastest, especially for powers of 2. So this is, 2 to the 20th. The FFTW approach on that pretty long data set is even faster than the Welch's method of averaging a bunch of smaller FFTs. But when there's prime numbers, the Welch's method is the fastest. And then here is the actual results of these various FFTs I calculated that I'm comparing. So you'll see here, I'm going to start with just the Welch's method and the NumPy and FFTW. You see there's no difference in the plots here. They're plotted exactly on top of each other. They're the same output, FFT, but it does take a little different time to compute it. One thing you'll notice, though, is this is one of my hesitations and then reasons why I dislike FFTs is it will only do, it has trouble if it doesn't have a complete number of cycles in the time range. And we have a blog on this leakage in the frequency spectrum, whereas some of these lengths of time, they have a good number of cycles, and so they pick up these peaks where we expected to see at 10 Gs, and this one's seeing it at 9 Gs. This one's seeing it around 8 Gs for these 3 different sine waves. But then some of the lengths work out kind of funny, so we get misalignment in the frequency range, and so you get this leakage into other frequencies, and you don't get that peak that you're expecting to see at your sine wave, amplitude. Now, when we use this Welch's method, we get the benefit of averaging a series of FFTs together, and now you see pretty consistent results. Well, very consistent results regardless of the length of the time. And I think that's pretty impressive, and this is a nice way to compute an FFT. You see here, it's again the same thing for everyone, and it's a peak exactly at 10 Gs, peak exactly at 9 Gs, or at 8 Gs we're here. But now what happened down here? Well, I have a bin width of 0.5 hertz. So I'm computing an FFT at 100 hertz, 100.5, 101. But I made it in this sine wave, it had a frequency of 100.25 hertz. So that's why I have 2 peaks here, one at 100 hertz, which is 4 Gs, and the other one at 100.5 hertz, which is around 4 Gs. So together it's 8 Gs, but we kind of missed that. So hopefully you're following along and understand that. But the big takeaway here is that the Welch's method, if you don't care about phase, is going to be the fastest, as well as give you results you expect. And allows you to explicitly define your frequency resolution, as opposed to being kind of required to use whatever the inverses of your total length of time. Okay, now let's get to some more real world data and vibration data with random frequency content. So here I'm loading in now a time series, and it's again reading CSV, so it's not data from our device. It's just loading in a CSV. But this CSV is a time history that has a PSD that matches this NavMat PSD test standard. So I read that in, and then I added, though, on top of it a few sine waves. So it's called sine on, or it's called the tone, sine tone on random. And now I plot that over time with this max envelope. Again, that's plotting basically a shaded area. So it doesn't have to plot all the data points. And then this one is plotting the time history around the peak. And you see they're all pretty similar, but they do have some deviation depending on this sine tone of added. So now let's compute the FFT using the Welch's method. And we see a peak exactly at 2 Gs at these different frequency ranges. So that's good. And we have some other content here with the random other frequency bins. And this looks about right, but we'll see here that this is where the FFT really starts to struggle, is when we have random data. What am I doing here? So I am comparing, I loop through and I computed this FFT for different bin widths in my, that I'm specifying, as well as different lengths of time. And the nice part is the peaks are all at 2 Gs, which is good, but the other frequency content, it gets impacted based upon what I define as my bin width, as well as my length of time. And that's problematic. That means, this is the same acceleration time history, it's just computing a little differently or slicing it, not maybe just 1 second versus 10 seconds, but they should have resulting frequency analysis that looks similar. But with an FFT, you may conclude that these are two different environments when in fact they are the same. So that's the big issue with PSDs, is when you don't have perfect sine waves and perfect resonances, the other frequency content can become misleading. The benefit of a PSD is that density. So regardless of the time range we use, the bin width, we should see consistent results. So I do that same analysis now with the PSD, and you see as the bin width gets wider, my amplitude stays the same in the PSD, yet it just becomes smoother. And as well as the length of time, as it gets longer, same thing, it just gets smoother. Yet my my amplitude was correct. Now you do notice the peaks, at those specific frequencies that I added those sine tones, they come down, but that's because my bin width is wider, the density, I have a wider area or wider length of frequency there. So it's maintaining a constant density. And that's what PSDs are doing. So now a lot of you asked, you have random data, you want to compute a PSD, and then you want to bring that into a Shaker's table of some sort. And so you have a long PSD like this up here. You're not going to necessarily enter this into a Shaker. There's 4,000 points. That's kind of a lot. So there is a method that we have here called 2-octave, where we compute the PSD with the linear spaced bin width, and then we give it into another function that we created, 2-octave, where you specify a frequency start and a bins per octave, and then you get a very coarse and logarithmically spaced PSD that you could enter into a Shaker table. Now, Becker and I were talking this morning, and we know a lot of people want to kind of get all the way there and specify maybe 4 breakpoints or 5 breakpoints and get an optimal PSD for that off of their experimental data. And Becker had some good ideas, and I think we're going to try to add that into our library in the coming weeks ahead. Now, just a little nice thing about PSDs is once you can take the area under it and you get the cumulative GRMS. And when you plot that, you can see, you can kind of nicely see differences of resonances and things like that and how they impact the overall RMS. So that's a nice little benefit. All right, let's do a couple other vibration sets and make it really simple, because I know that was a problem in my last webinars. I've kind of added too much analysis and I think I lost some people. So here's a bearing data that I covered in a blog. There's 4 data sets for different bearing fault conditions. So I load that in as a CSV. It's again, not necessarily data from our devices. And then I do this rolling dashboard calculation, or plot rather. And now I can do the PSD. So once I have the time history, I add that into this function. I specify a bin width. I'm saying 10 hertz here, and then I plot it. And here, you may have noticed sometimes I've been saying the template of enDAQ light. We have two templates in our style guide here, the dark theme and the light theme. So I'm mixing up one between these plots. And here's the PSD off that time history. Of the 4 time histories, you notice the normal bearing has some more content or more energy at lower frequencies and much less at higher frequencies compared to those fault conditions. And it's pretty obvious to see in the power spectral density, especially when I made it a relatively coarse bin width. So I don't have it just kind of a shaded mess. Now let me pull in another data set. This was generated years ago, back in like 2016. I put it on my car engine and I drove to work. And so I'm again using one of the built-in functions in our library for data off of our devices to load in this file. And I'm getting the channel 8, which is the analog accelerometer. And here I'm getting time data that isn't as seconds, but actually is date time. So I can actually see the date and time, which is nice. I did apply here a high pass filter to remove the DC offset, and then I plotted it. Now, if I do, this is the power spectral density of that whole time. But if you notice up here, I'm driving on I lived in Charlestown at the time, basically inside of Boston City proper, and then I have to drive outside the city, get on the highway, and get off the highway and get to my place of work. So my car engine is revving at a various number of different RPMs, and you wouldn't necessarily see that when you compute just the PSD off the whole time history. You'd want to do a spectrogram. And so we have a function in our plot module, Octave Spectrogram, which has the benefit of allowing you to get a logarithmically spaced frequency bins. I think we want to add some more functionality to the spectrogram to allow you to do linear spaced, maybe make this into a waterfall plot, things like that. But you can see here, it's a pretty easy API. You give it the channel you want, the window length, that's length and time, the bins per octave, the frequency star, and the max frequency. And now you get this spectrogram. So you can see when I'm on I assume this is when I'm on the highway and I'm revving the engine, I'm accelerating, I'm maybe driving a little erratic, and I get to work safe and sound though. Once you can pull from this data set, the return of that spectrogram call is to actually get the max frequency. So you can plot that over time too. So that can be helpful. And I could probably multiply this by 60 and say this is the RPM of the engine through my drive. All right, I'm going to launch another poll question. So I just went through a lot of FFT and PSD stuff. And my question to you is, should we add some more functionality to do FFTs in our library? We have the function to do the PSD, but there isn't explicit functionality to get a FFT. And if you're interested in that, what functionality would you like to see added? Do you like that method I showed you where we're using Welch's and we're letting the user define a bin width, so the frequency resolution? Or do you like using NumPy's kind of standard approach? Or do you want some optimized way for speed, or all the above, or none? So I'll give you a moment to answer that. So pretty overwhelmingly, I'll end the poll. You guys want to see us add some functionality for PSD. So I expected that, and that's good though to see and be confirmed. And it looks like it's pretty good range though. If you like that defined bin width, but you also want things that are more traditional with phase and optimized for speed. So we'll definitely take that in and add some more functionality to meet that need. Okay, flying along, 30 minutes. So now let's look at some shock data. So I'm going to look at two data sets, one from a punching bag, someone's punching a punching bag with one of our devices on it, and another from a shock test at a Navy test lab. So this is the first data set, and this is from our device. The next one I'll show loading from a CSV. Again, you're using that getDAQ and the two pandas function. I'm plotting this max envelope, so I get I'm plotting not necessarily all the data points, but when it's zoomed out, it looks the same as if I were to plot all the data points. And you see there's 3 impacts. And then we have this function around peak, where we'll find the maximum across all the columns, and then plot the user's specified number of points, which I want 1,000 data points plotted here. There's another parameter in this, which is the leading ratio. So it's defaulted to be 0.5, which means it's going to put the peak exactly, midway through my window of 1,000 data points. But typically, when you're doing shock testing, you may care more about what happens after the event. So I'm saying I want 20% of my window to come back as before the peak, and then 80% as after the peak. So you can play with that, though. There may be sometimes you care more about what happened before the event than after. Okay, so now let's do the shock response spectrum calculation. The first thing is, when you do a shock response calculation, you're calculating for a given number of natural frequencies. So you need to specify which frequencies you want to calculate. We have a function in our library.logfreq. So you give it the data frame, the time history. So I'm saying I'm going to do it just for that 1 second around the peak event. And it will find the sample rate, and then plot up to the Nyquist frequency, and it also sees the period of time, and that uses that as the starting frequency. And then you say the bins per octave. So I want 12 bins per octave. Now I pass these frequencies in, the damping ratio, the mode SRS versus PVSS for the pseudovelocity, and I give it the time history, and it returns that shock response spectrum. So here I plot the shock response spectrum, pretty straightforward, and you see the shock response spectrum of that punching bag data in the x-axis, y, and z-axis. Now I'll repeat that same calculation for pseudovelocity. It's the same function call, and though instead of saying mode equals SRS, I said mode equals PVSS. I do have to scale it though. We do no unit conversion in any of our calc functions. So this is basically Gs per second. So I need to convert that to inches per second, which is right here. So I go from Gs to meters per second, and then from meters per second to inches per second. And then I plot that. Now I'm going to do the same thing on another data set. Again, I'm loading from a CSV file. Again, highlighting half of you have our devices, half of you don't, and that's fine. Our open library does not need you to be using data from our devices. So you load in a CSV or another type of data set, and I plot it. This data set is from some barge testing. If you guys do some government military testing, Mil Standard 901D is some heavyweight shock. That's pretty, you put your system on a barge, and then you put an explosion under it. And there's some videos online, you can Google it, it's pretty cool. And we had to do some testing for some of our equipment. We sell sealing systems to the US Navy, and those need to be qualified. So here's that shock event, pretty aggressive, 600 hertz. If you remember from the punching bag, there's a peak of 60 Gs. Now on the Mil Standard 901D, 600 G peak. And here's the time history at the beginning. You see it's pretty high frequency, and it's going 600 plus or minus. It's not just there was one little data point that hit 600. It was pretty consistent. Now I'll do the same calculation. I have the time history. I want to get a number of frequencies log spaced. Here I'm going to expressly define, I want the starting frequency to be 1 hertz though, because my data set is only 0.35 seconds or so, which means I have to zero pad to get frequency content down to 1 hertz, which we handle in this calculation, but we call that out here. There's an error that this is too short, and you may want to get a longer data set, but in any case, we'll zero pad it. We do the shock response spectrum, same call, you give it the time history, the frequencies you want to calculate at, the damping ratio, mode SRS, and then you plot it. Here's the plot. And then you do the same for the shock response spectrum. You just say mode PVSS, and then you plot it. Now, here I want to compare the two. So I'm just going to kind of gloss over what I did exactly, but I just compare those two plots. This is a punching bag SRS data, and here's the mil standard 901D. And you'll notice that for much of the frequency content, everything less than about 100 hertz or so, they have a pretty similar response. It's really the high frequency content that is much different from the big heavyweight shock. And if I look in the pseudo velocity, you see that kind of hold true, is that they both have a peak pseudo velocity, which we typically use to define damage potential of around 150 inches per second. Yet one was a 80G shock event, the other was a 600G shock event. And so this is just a small reminder that looking just at the peak acceleration doesn't necessarily tell the full story. You want to do a shock response spectrum, you want to do pseudo velocity, and you see here a lot of the content that contributed to the high acceleration amplitude are up at 2,000 hertz, which may not really matter for your system. Okay, how am I doing on time? All right, this is, a lot of you said you wanted to see peak findings. So you have a data set that may be many different transient events. You want to identify them and isolate them. So here first, I'm just loading in the data and I'm plotting it. This is on some robot and they're driving around and they're hitting some bump. I don't really know exactly what they're doing, but I know it's a robot and they're hitting bumps. So SciPy has a function called find peaks. So I give it the data set I want. So I'm saying I'll use the bumps, but it's focus on the y-axis data. I also look at the absolute value. I don't want to only care about positive peaks. I'll just look at both positive or negative. Then there's a distance parameter you can specify. There's other parameters you can specify, prominence and things like that. But I want to say here, I want them all, every peak to be at least 5 seconds apart. So it doesn't kind of double count things that are close together. And I want the peak to be at least 8 Gs. Okay. And so I get a return of an array of indices that I can then plot. So I'm saying, all right, now I want to plot, I'm going to add to this plot these circles at the peak time index, which is the time, and then the actual value. You see some of these are positive shock events, some are negative, and they come right at that peak event. And if I plot just the time history at one of the events, you see it's exactly at that peak. Okay. Now we're going to do a shock response spectrum or a pseudo velocity on the full time history, which I do here. One thing that kind of surprised me and may surprise you is the worst pseudo velocity is in the x-axis data. But when we go up here, the x-axis peak acceleration tended to be less than the y-axis. Again, reminder, the peak acceleration isn't always the full story. You can see here, comparing the two, that there's a longer, lower frequency component to the x-axis than the y-axis. And that's why y-axis has a higher acceleration, but in the velocity, it has less velocity. And velocity is, 1/2 mv squared. There's what the energy is. But there's about 5 or 6 events here. What if I want to focus on, do a shock response spectrum on each of those events, which I do here. I won't go through the code because we don't necessarily have the time. But now I plot the shock response for X, Y, and Z axis at every one of those peak events. And you see here, it's pretty consistent from event to event, which is good. But there is some deviation. And I wanted to highlight that, one event here is with the 23.5 G peak. And here's the one that has a 12.8 G peak. So for the one that had the 12.8 G peak has an actual higher pseudo velocity. So again, remember, half the acceleration amplitude, but actually double the pseudo velocity. Not quite double, about 20–30% more. Okay, almost done. Last thing I want to highlight is the preview of our batch processing module. And so this is currently available. When you download the library, it's there. It's kind of in a beta though. We're still adding some functionality and adding some bug fixes. But in a local notebook, I executed this code. The first thing was I got a list of files in a folder. Batch right now is only working on devices or data from our devices for now. We will add functionality at some point so you could load in a bunch of CSVs or something as well. Then once I have all these file locations, I use this batch builder, and there's a various number of things we can do. We do shock response spectrum, power spectral density analysis. We calculate these metrics, and you can kind of tailor how you do this with this get data builder. And then you get the output, and I save the output as pickles so that I'm loading it in here, and I'll show you what kind of the results look like. I do want to highlight, though, I did have to add this line of code to basically strip away the full file name because I didn't want to show the folder location because that contained the customer name. So now I load in the metrics. So this is the batch processing of, there's 5,000 files here. I loop through them, and I calculated all these metrics. So RMS acceleration, RMS velocity, RMS displacement, peak absolute acceleration, peak pseudo velocity, RMS angular velocity, and then the average temperature. But all these calculations are done for the x-axis, the y-axis, the z-axis, and then a resultant. So here I'm going to plot a few of them. I won't plot all the metrics. I'll focus on, RMS acceleration, RMS displacement, and peak acceleration here. And you see how this changed over, about a month's worth of testing, 5,000 files. You could identify here, this is my macro trend, but maybe you want to focus. You see here in the hover text, the file name is specified. So you could then dive deeper into that specific file. One of the other elements of that batch builder was it computed a bunch of power spectral densities. So I'm going to load that in. I do some manipulation here to round my frequency bins and focus on one axis, the y-axis. And so now I want to make a waterfall plot. Let's see here if I. So again, I only focus on the first day because there's 5,000 files. So I create this 2D waterfall plot. You can see each one of these lines represents one of those files. And you can see how that's changing from time to time throughout the test. Now you may want to see it in a 3D view, which this crashes, so I saved it over here. So this is a 3D waterfall plot, and you can see, I color coded it. So as it gets from blue to red, that means it's going farther and farther in time, and you can see how the frequency content changes. It's pretty consistent, although there are periods that move a little bit. So how do you see that movement? You can also make an animation, which I'm doing here. And I'm going to gloss over this because we're running out of time. And this is showing how that power spectral density changed over the 20-day test, although I'm only showing the first day because there's so many files. Okay, with that, I have the last poll question, and then I will open up to more questions, which is, that's a wrap. Are you ready to start yourself? One, yes, you're good to go. You're going to start using the library now, or no. You really like what you see here, but you still want to see some more examples, some more documentation, or your use case is maybe a little unique. You'd like to see us help you get started, and then once we give you a starting point, you can take it from there. Or are you just not interested in writing your own code? You want us to give you an executable, or neither. You just want to do your own thing. And I will let you finish that overwhelmingly, which is good. You guys want to use this, which is great, but you would like to see us add some more examples and documentation, which we plan to do. So with that, Tina, we're 45 minutes in. I think we can open up for some questions if they are any outstanding ones.
All right, so we do have a couple of questions. The first one, could you answer what is the influence of SNR of input signal on results of presented procedures of shock response spectrum?
I don't know if I can answer that one. What was that, SNR?
Yes, of input signal on the results presented of the procedures of the shock response.
Oh, yeah, that might have been a similar question that came up last time. That people want to see what was the standard Becker and Connor is some ISO standard. we have looked into that. We do think we're in compliance with that. There may be a small thing we want to change to be explicitly doing exactly what that ISO standard is. But remember, it's open source, so you can go look at the source code on GitHub and see exactly how we're calculating it. But I don't know, more to come on that. I know we need to be in compliance with that ISO standard. I can't say the results are in compliance, but we can change some of the ways we calculate it.
Actually, do you mind if I
Sure.
add a quick thing? Sure. So, Michael, it sounds like you're asking, at least in part, what's the impact of noise on the shock response calculation? And I think, like a lot of other calculations, it just, the more noise you have, the more it's going to distort your result. I can't say that I've played with adding noise to signals and then seeing how it changes the pseudovelocity directly, but that's kind of my impression. And as far as how it distorts it, it'll depend on the kind of noise in your system and some other factors. But yeah, I think like any other calculation, the better your signal to noise ratio is, the more pure your output is gonna be.
Yeah, I guess another point too is you would, one of the benefits of the SRS is you're looking in the frequency domain. So if your noise is in a certain frequency range, it may become more obvious what's noise and what's real. But yeah, definitely play with that and see the result. But it's gonna matter, I guess, how much noise you have and what frequencies those are at.
Similar, well, in the same vein, I suppose. Is there something with how to deal with with noise, a method to clip specific events from a huge data set?
Well, I mean, the first thing you can do, which is just applying a digital filter, and I showed an example of that. And if you go to docs.enDAQ.com, that's where we have some digital filters, so you can remove frequency content below or above a certain cutoff frequency. If you want to remove a specific event, that's where I think our batch processing will really come into play and help, where you could, if you have a long time history, that's one thing we do need to add to the batch processing too, is either do a bunch of explicit files, or if you have a big file, kind of separate the file into a series of segments, and then you'd be able to kind of, you could see an outlier in here and then potentially just remove it when doing the power spectral density. So I think batch processing is going to be how you address that in the future.
So that concludes the questions that we've gotten that haven't already been answered by the software team.
Okay, great. Well, yeah, so just to preview what's coming next is our next webinar is we're going to be going through the batch processing library and go through a lot more examples there. And then beyond that, we'll be doing some stuff to show you can customize reports in the enDAQ cloud. But between now and then, I did want to highlight, and I forgot to mention it, is one of the benefits of GitHub and open source is it's public and you can look at issues, comment on them, vote on them. So if you want to see some functionality that isn't already in the library, I do encourage you to come here, maybe post a feature request. We can see it. We can write code and comment and have a discussion about it. So be aware of that and monitor that. But we will always be adding more and more functionality. So do keep yourself abreast of our updates. So big update coming next is batch. Between now and batch, though, we will add some more support for FFTs that we just got overwhelming requests for. And again, we're here. Our customer success team is here. If you have questions, we're happy to help get you started. Thank you, everyone. I'll give it to you, Tina.
Great. Thank you very much. That was great. Thanks so much for attending today. We hope you found this webinar helpful and informative and that you're ready to start using Python in our enDAQ open source library to customize and adapt your shock and vibration analysis. If you have any other questions or think of something later, don't hesitate to contact us. We'll send out an email in the next few days with a recording of this webinar and links to some helpful resources. Just a reminder that this webinar is part of our Python for Mechanical Engineers series. As Steve said, our next webinar will be on batch processing early in the new year. You can sign up for our webinar notifications and we'll send you the registration information as soon as it's available. Finally, once we close the webinar, a feedback survey will launch. Like I said earlier, we'd love to have your feedback on this webinar so we can improve our content and ensure that we're providing relevant resources that can help you with your analysis. Again, from all of us at enDAQ, thanks so much for joining us today. We really appreciate your time and hope you found this helpful. Take care. Bye.
Bye, everyone. Thank you.